Welcome to the deep dive. We're here to unpack the big ideas and maybe, uncover a few surprises along the way. Today, we're diving into something really fascinating, a way of exploring the cosmos that sounds simple but tells us so much. We're talking about stellar occultations. Okay, let's unpack this. What exactly is a stellar occultation? And what can that little dip in starlight actually tell us?
Well, simply put, a stellar occultation is when an object in our solar system, think maybe an asteroid or even a moon way out there, passes right in front of a distant star.
Huh.
Just for a moment, it blocks the star's light from our perspective here on Earth.
Okay, a cosmic blink.
Exactly. And that brief, measurable drop in the star's brightness, it's incredibly useful. It's sort of like a cosmic shadow puppet show, but scientifically rigorous. It lets us figure out the occulting object's exact position, its size, its shape.
Size and shape, just from a shadow.
Yeah, precisely. And sometimes even more subtle things like, is it a binary? Two objects close together? Does it have an atmosphere? We actually got hints about Europa and Triton's atmospheres this way just back in 2021. Or maybe it has rings or moons or even big mountains or valleys topography.
That's amazing, but I mean, predicting when and where these things would happen, that must have been almost impossible historically, right?
Oh, absolutely. You've hit on a key challenge. Before, let's say before the Hipparcos satellite back in 97,
Hmm.
our knowledge of star positions and, the orbits of asteroids and things,
Yeah.
it just wasn't accurate enough.
So predicting an occultation was like pure luck.
Pretty much. It was incredibly difficult to know if you'd even be in the right place on Earth to see one. But that's where the European Space Agency's Gaia mission really changed everything.
Ah, Gaia. Okay.
Gaia has just revolutionized this whole field. It's created this incredibly dense, incredibly precise map of, well, billions of stars and countless solar system objects. So now, identifying and predicting these occultation events pretty much anywhere in the world, it's vastly easier. It's been a complete game changer.
And I understand it's not just the big professional telescopes involved either. What about amateur astronomers?
That's a great point. This is actually a hugely collaborative field. Amateur observers are crucial. They're spread out all over the globe. They're dedicated, and they often coordinate through projects like the Lucky Star Initiative.
So it's a real community effort.
Totally. And then you have these online databases like the ones run by the Rio Group or NASA's planetary data system where all this data gets collected and shared. It really takes a village.
Right. And this ties into the bigger picture of understanding our solar system.
Exactly. One of the really big goals in planetary science is figuring out how our solar system formed, how it all came together. And Gaia-enabled occultations, they've basically, well, unlocked the door to studying the outer solar system in a much more widespread way. I think Mark Bowie, who knows a lot about minor planets, basically said Gaia just opened up that whole area for us.
So since Gaia really kicked this into high gear, maybe around 2021 or so, what have we actually learned about those distant, mysterious objects out there?
Oh, the results have been fantastic. We're getting precise dimensions for things that were just, pinpricks of light before.
Yeah.
We've learned more about Neptune's big moon, Triton, its shape, its atmosphere, Saturn's weird moon, Phoebe, too.
Okay.
And beyond the planets, dwarf planets like Pluto and Haumea, even Haumea's little moon, Hyaka. We're seeing details about surfaces, finding unexpected rings, plus a whole bunch of those really distant trans-Neptunian objects, TNOs and the centaurs that orbit between the giants.
Like Chiriclo, the one with rings.
Exactly. Jericho and its rings were a huge discovery refined by this. And others like the elongated 2002 GZ3D2 or a Keklis. It's just revealing this incredible diversity out there. These objects aren't uniform at all, which makes us rethink how things formed. And researchers are now using things like the SRA analysis package to compare sizes from occultations with, say, thermal measurements.
Okay, so we're getting amazing detail on the objects doing the blocking, but you mentioned slipping the script. What about the stars being blocked? Can occultations tell us something new about them?
Yes, absolutely. And this is, I think, a really cool, somewhat surprising application. We can actually use these events to help determine the mass of stars.
Stellar masses. But aren't those incredibly hard to measure?
They are. They're fundamental, telling us how a star lives and dies, but measuring mass directly is tough. Usually, we need an orbital binary system, where we can watch two stars orbit each other and apply Kepler's laws. That needs really precise long-term observations.
Right, you need to see the dance.
Exactly. But occultations can offer a different path, sometimes a more direct one.
Interesting. Do you have an example of how that worked?
Yeah, there's a great case, a star called HIP 36189. It's a K giant, reasonably bright. Back in 2003, it was actually discovered to be a binary star, precisely because an asteroid 74 Interamnia passed in front of it.
The occultation revealed it was two stars.
Kinda, yeah. The light curve looked weird, suggesting two components. Then astronomers combined that occultation data with the orbital period, how long they take to orbit each other, which Gaia later measured very accurately, about 2.6 years. And putting those together, they could calculate the individual masses. One star is about 3.9 solar masses, the other around 3.5.
Wow. Just from the occultation and the orbit.
Yeah, a really neat result for a system that would have been much harder to pin down otherwise.
Okay, so that's stellar mass. But here's where I think it gets really mind-bending. You're saying we're not just probing the asteroid, but the star itself. How does that brief dip tell us about the star's physical size?
All right, this is the main deep dive focus. A star's physical diameter is, well, it's critical. It helps determine its temperature, its actual brightness, its evolutionary stage, basically fundamental stuff.
Okay.
Now, in theory, if you know a star's angular size, how big it looks in the sky, and its distance, you can calculate its physical size, its radius. But measuring that angular size directly, that's notoriously difficult.
Nope, too small.
Exactly. Stars are just incredibly far away. So even though some are huge physically, they appear as minuscule points of light. We're talking typically less than 1 milliarc second across.
A milliarc second. That sounds incredibly tiny.
It is. Think of a degree in the sky. Divide that into 3,600 arc seconds. Now divide one of those arc seconds into 1,000 tiny slices. That's a milliarc second. Most stars are smaller than that from our viewpoint. Too small for even our best telescopes to resolve directly as a disk.
Okay, so we need clever tricks. You mentioned things like interferometry or using eclipsing binary stars.
Yeah.
And didn't people use the moon for occultations too?
Yes, exactly. Those are other important methods. Interferometry combines light from multiple telescopes to effectively create a much larger one, which can resolve some stellar disks. Eclipsing binaries give us info when one star passes in front of its partner. And lunar occultations, when the moon passes in front of a star, have been used for a long time. They work on a similar principle to asteroid occultations.
How does that principle work, the diffraction thing?
Precisely. It's all about analyzing the diffraction pattern in the shadow. As the edge of the moon, or an asteroid, passes across the star, the light waves bend slightly around the edge. This creates a pattern of faint ripples, like light and dark bands, in the starlight, just as it's being blocked or uncovered.
Okay, light ripples.
Yeah, and analyzing those ripples requires extremely fast and precise measurements of the star's brightness, what we call high-speed photometry. Lunar occultations can get us down to angular diameters of about 1 milliarc second, especially in redder light where the moon's glare is less of a problem. Yeah. But pushing below that 1 milliarc second limit has mostly relied on interferometry, which is technically very challenging and, frankly, expensive.
But you mentioned something new, something unexpected, using telescopes built for something else entirely.
That's right. This is a really fascinating recent development. It involves the VERITAS telescope array.
VERITAS, aren't those gamma ray telescopes?
They are. VERITAS stands for the Very Energetic Radiation Imaging Telescope Array System. It's a set of 4 huge 12-meter reflectors down in southern Arizona. Their main job, their whole design purpose, is to detect the incredibly faint, brief flashes of blue light, Cherenkov light, produced when very high-energy gamma rays from space hit our upper atmosphere and create particle showers.
Okay, so they look for faint flashes from gamma rays. How on earth do they measure the size of a regular star?
Well, it sounds like a paradox, doesn't it? These telescopes weren't really built for traditional optical astronomy. Their mirrors, while huge, have what astronomers call modest optical quality compared to, say, Hubble or Keck.
Right. Not designed for sharp images of stars.
Not primarily, no.
Yeah.
But here's a clever bit. Because their mirrors are so large, 12 meters each, they are fantastic light buckets.
Light buckets?
Yeah, they can collect a huge amount of light in a very short amount of time. And that's exactly what you need for that high-speed photometry we talked about, to see the diffraction ripples during an occultation. So researchers realized they could use VERITAS's light-gathering power during asteroid occultations.
Ah, using asteroids, not the moon.
Yes. And here's a key advantage. Because the asteroid is much farther away than the moon, the diffraction pattern it casts is actually sharper in a way, or at least allows for finer detail to be extracted. This lets them push below the 1 milliarc second limit that lunar occultations usually hit.
Wow, so using gamma ray telescopes to look at asteroid shadows lets us measure stars smaller than we could easily measure before.
That's the breakthrough, yes. It really shows how sometimes you can get amazing results by repurposing tools in ways nobody originally intended.
That's incredible scientific ingenuity. Can you give us some real examples? What have they actually measured with VERITAS?
Sure. They've reported a couple of really successful events using Gaia's super precise positions to know exactly when and where to look. First one, February 22nd, 2018. An asteroid called 1165 Impruneta passed in front of a star, TYC 55172271. It's about 10th magnitude, so reasonably faint.
And what did they find?
They measured the star's angular size as 0.125 milliarc seconds, plus or minus about 0.022. Tiny. Then, using the Gaia distance to that star, about 820 parsecs, so quite far they calculated its physical radius, came out to about 11 times the radius of our sun.
11 solar radii, so a fairly large star.
Definitely a giant star, yeah.
Okay, what was the other one?
The second event was May 22nd, 2018. This time it was asteroid 201 Penelope, which is about 88 kilometers across. It occulted another star, TYC 2787481, around 9.9 magnitude. Here, the measured angular size was even smaller, 0.094 milliarc seconds, with a small uncertainty.
Even tinier on the sky.
Yep, and this star is closer, about 215 parsecs, according to Gaia. Doing the math, that gives a physical radius of about 2.17 times the sun's radius.
Okay, much closer to a sun-like size, maybe a bit bigger.
Exactly. And what's really cool about this result is that Gaia itself, through its complex data processing, specifically something called the flame catalog, also provides a very precise radius estimate for this star and the VERITAS occultation result. It was an excellent agreement, almost spot on.
That's fantastic confirmation. It shows the technique really works, and accurately.
It really does. It validates the whole method beautifully. And looking ahead, the potential is huge. Estimates suggest that even a single telescope, like one of the VERITAS units, could catch maybe 5 occultations of 10th magnitude stars per year. And if you go fainter, to 13th magnitude stars, that number jumps to almost 1 per week.
Wow, that's a lot of potential data.
A massive increase in our ability to directly measure the sizes of stars, especially types or evolutionary stages that are hard to get with other methods.
It really is astounding when you stop and think about it, how this simple alignment, one object passing in front of another, can tell us so much. You know, from the shape of a tiny moon's atmosphere way out past Neptune to the actual physical size of a star hundreds of parsecs away, all thanks to incredible tools like Gaia giving us the map and then clever uses of other instruments like repurposing gamma ray telescopes.
It really highlights the ingenuity involved, doesn't it? How astronomers figure out ways around these huge observational hurdles. And the power of combining different data sets is key here. Gaia's positions plus Veritas's light-gathering ability equals insights we couldn't easily get otherwise. What's really fascinating, I think, is how looking through one object, the asteroid, gives us this incredibly clear picture of something else entirely, the star behind it.
Yeah, seeing through one thing to understand another.
Exactly. It just shows that sometimes the biggest breakthroughs, the clearest views, come from the most unexpected angles.
Which leads us perfectly to a final thought for you, our listeners, to maybe chew on. Think about what other fundamental things about the universe are still really hard for us to measure directly. What properties of stars or galaxies or planets remain elusive. And then maybe consider how some other seemingly indirect technique, some unexpected observation, or maybe even another repurposed instrument like Veritas, might hold the key. What else could we potentially see through to get that next big aha moment in understanding the cosmos?